Hello there, everyone, students, lovers of chemistry out there. This is your favorite chemistry tutor, David, the billionaire teacher who takes the mystery out of chemistry so you can make history. I'm logged on today on the 15th day of our free chemistry classes with David, and today's class happens to be for the SS3 section of the senior secondary school. So today we're going to be going into the introduction to redox reactions, and I'm super excited to be here with you, and I'm sure you're pumped up for what we have in store for you in today's class. So just one quick notice. I want you to sit back, relax, and enjoy every bit of what I've got for you in today's video. Trust me, it's going to be broken down into the simplest way that you can understand. So let's get right into what we have for today's video. All right, now, so we have the outline of what we want to do as far as redox reactions are concerned. So let's go right into the introduction for today's class. First things first, we want to have a basic understanding about what redox reactions are. So that will serve as the foundation for what we'll be doing in the as far as this whole topic is concerned. So what are redox reactions? Before reading what's on the screen, I want to break it down this way. Redox reactions are actually, the word redox is actually a combination of two words, RED and OX. RED over here stands for reduction, and OX over here stands for oxidation. So to define this in the simplest way that anyone can understand, redox reaction is a reaction where both reduction and oxidation are occurring at the same time. Scientists also define it as reactions or chemical reactions that involve the transfer of electrons from one substance to another. So the word redox is a short form of reduction and oxidation. In every redox reaction, one substance loses electrons. And when substances lose electrons, we call it oxidation. And when another substance gains electrons, we call it reduction. Now, think of it like this way. When you transfer money to a person, you get a debit alert while the person gets a credit alert. Now, the two processes happen at the same time. So redox reactions are kind of like that. One substance is getting a credit alert by gaining electrons. Another substance is getting a debit alert by losing electrons. So the substance that gets the debit alert in this case is the substance that is oxidized or undergoes oxidation. And the substance that gains the electrons or gets a credit alert is the one that is reduced or gains or undergoes the process called reduction. So basic things, reduction is a reaction. Redox reactions are reactions where both reduction and oxidation are occurring at the same time. It is also important to note that both processes happen simultaneously or together. When one substance is oxidized, another substance is reduced. So let's define it this way. Oxidation is the loss of electrons by an atom, an ion, or a molecule. So when electrons are lost, we say oxidation has occurred. And when electrons are gained, we say reduction has occurred. So now that we have defined both processes and what they entail, let's move into the next thing that we have on today's lesson. Since we know that redox reaction involves the transfer of electrons, it is important to know what happens to electrons when redox reactions happen. So at the heart of every redox reaction that is taking place is the transfer of electrons. Now look at this equation on the screen right now. Magnesium is one of the elements that is taking part in this chemical reaction. Now, on the left side of the equation, you can see magnesium over here on the left side. And on the right-hand side of the equation, magnesium has changed to now have a charge of 2 plus, What does this mean? This charge here, 2 plus, simply means that it is now positively charged, or its oxidation number has increased to plus 2. I'm going to be explaining all of these concepts and what they mean as we progress in this topic of redox reactions. Now, you can notice with me that magnesium over here loses 2 electrons. And when it lost 2 electrons, it moved from Mg to become Mg2 plus. The 2 plus over here is simply telling us that 2 electrons have been lost. And so when electrons are lost, remember I said that that is the process of oxidation. And when electrons are gained, that is the process of reduction. Now look at this over here. The second element that is taking part in this chemical reaction is copper. And on the left-hand side of the equation, we have copper 2 plus, which is a positively charged ion. And on the right-hand side of the equation, we have the copper atom. Now, over here, you can see the oxidation number is plus 2. And over here, copper doesn't have an oxidation number, or the oxidation number is 0. In other words, it gained 2 electrons, and those 2 electrons that it gained reduced it from copper 2 plus to become the copper atom. So this is a perfect example of a redox reaction. This guy over here was oxidized, and this one over here, copper, was reduced. We're going to be explaining in simpler details how to know the ones that are reduced and the ones that are oxidized. So here is a helpful tip that I want you to um, keep at the tip of your sleeves. This tip shows clearly how elements donate electrons and how others lose electrons. Always use this acronym in order to remember oil rig. You can see I have the picture of an oil rig over here. Okay, so whenever you remember this acronym, oil rig, OILRIG, you just simply say O stands for oxidation, I stands for ease, and L stands for losing or loss, whichever one you choose to go by. So you simply say oxidation is losing, and then RIG, reduction, is gaining. So those are the two acronyms. Oil rig, oxidation is losing or the loss of electrons, while reduction is gaining or the gain of electrons. Now that we know what oxidation is and what reduction is, an important concept you need to be familiar with is the concept of oxidation numbers, because when substances lose electrons and when they gain electrons, there is something that changes. If a substance Let me write it out on the screen. If a substance loses electrons, the oxidation number changes. And if a substance gains electrons, the oxidation number also changes. So now that we know what changes when a substance gains or loses electrons, it is important to know what an oxidation number is. An oxidation number in chemistry is also called the oxidation state of that element or substance. It is a number that is assigned to an atom in a chemical compound that shows how many electrons it had lost, gained, or shared during a chemical reaction. Now, let me backtrack a bit to show you something. In the previous example where we saw an equation of a redox reaction, you can see over here Mg plus Cu2 plus yielding Mg2 plus Cu. Now you can see over here we have 2 plus. This 2 plus is the oxidation number of copper over here. What it is simply telling you is that the oxidation number of copper is plus 2, or it had lost 2 electrons. And over here on the right hand side, you can see copper. The oxidation number is not shown, or it is 0. So it is simply telling you that the oxidation number of copper over here is 0. So that is what oxidation number is. Now let's get back to the definition that we're talking about. An oxidation number is a number that is assigned to an atom in a chemical compound that shows how many electrons it has gained, how many electrons it has lost, or how many electrons it has shared during a chemical reaction. So that number is simply telling you through the oxidation number, you can just look at it and you can know if a substance has gained an electron, that oxidation number will tell you. If it had lost an electron, the oxidation number will also tell you. So that is why the oxidation number is an important concept we need to be familiarized with in the topic of redox reactions. So here is the importance of what the oxidation number is all about. First things first, it helps us to track electron transfer in redox reactions. It helps us to know, okay, where is the electron moving from and where is the electron going to? That is the first one. And the oxidation numbers also help us to determine which element is oxidized and which element is reduced. Remember from the equation that we just saw, where we saw magnesium plus copper yielding Mg2 plus Cu. The oxidation numbers over here show us that magnesium is losing electrons, which means it is oxidized, and then copper is gaining electrons, which means it is reduced through the oxidation number, of course. The oxidation number of magnesium over here is 0. Don't worry, I'll explain why. And you can see over here the oxidation number of copper is +2. And then over here, you can see the oxidation number of magnesium has increased from 0 to +2. And that means it is oxidized because it has lost electrons. And you can see over here, the oxidation number of copper is 0. It has reduced from +2 all the way to 0, which means it has gained electrons, which means it is reduced. So you can see how the oxidation number can help us to identify which element is oxidized and which element is reduced. Think of the oxidation number of an element. Think of it like a score, that tells us how charged an atom is. It's just like writing an exam. If a person scores 20 over 100, just by looking at the score, you can tell that the person will have an F. Is that correct? I believe it is. And just by looking by the score, if the person has probably, let's say 60 over 100, you can conclude that the person will end up having a B. And then if the person has 70 and above over 100, you can conclude that the person has an A. Just like that, you can conclude the grade of a person just by looking at his examination score. In the same way, you can know if an element is oxidized or reduced by looking at the oxidation number. Are we clear on that? Beautiful. I know we are. So now that we know what oxidation numbers are, there are certain rules that apply to the process of assigning oxidation numbers to elements, to compounds, and to ions. And we're going to be looking at them step by step. Rule number 1. The oxidation number of an atom in its pure element is 0. What do we mean? Whenever you see an atom, whenever you see an element or a molecule in its pure state. For instance, let's say we write the element oxygen, O2. There is no number anywhere like maybe 2 plus or 2 minus that is identified over it. So what we simply mean is whenever you have a case like this, an element or a molecule identified like this, automatically the oxidation number is 0. That is rule number 1. So if I write out an element, say hydrogen, for instance, H2, this is the hydrogen molecule. Automatically, the oxidation number is 0. Same thing applies to hydrogen, to sodium, Na. You can see there are no oxidation numbers identified anywhere, whether by writing a plus or a minus. So whenever you see this, you automatically conclude that the oxidation number is 0. That is rule number 1. Please do not ever forget that. The oxidation number of an atom in its pure elemental state is 0. rule number one. Rule number two. The oxidation number of a monoatomic ion is equal to its charge. What do we mean? Now, watch this. First of all, what is a monoatomic ion? A monoatomic ion is an ion that is made up of just one atom. So when you have one atom bearing a charge, you call it a monoatomic ion. Monoatomic ion. Okay, so what is the rule saying? The oxidation number of a monoatomic ion is equal to its charge. By the way, an ion is simply an atom, a molecule that bears a charge. The charge can be positive or negative. So for example, we have sodium over here, Na. And Na is not just written ordinarily like that. It is written with a notation, a plus notation above it. Now, this plus is telling you that there is a charge present. Not only is it telling you that there is a charge present, it is telling you that the charge is positive because plus stands for positive. Now that we have seen that, the plus there signifies that the charge is a positive one. So automatically, the element is monoatomic. We have just one atom of sodium. One atom of sodium, and the charge is plus or plus one. In chemistry, if the charge is plus one, we don't write it as plus one, we just write a plus. Okay, so now that we have one atom of sodium and the notation above it is a plus, automatically its charge becomes plus one, or its oxidation number is plus one. So that is why over here, we having Na plus, the oxidation number of sodium automatically became plus one. I know that you're following every bit of what we're doing in today's lesson. The next example that we have is chlorine Cl minus. Now, if this minus was not there, it will automatically mean that this chlorine is in its pure elemental state and its oxidation number will be zero. But now there is a notation above it, which is a minus sign. That minus sign is telling us that there is a charge and the charge is negative. And since it is negative, it means that the oxidation number will now be minus one, because I told you when all that we identify is just the sign, we didn't put any number, it automatically means that it is one. All right, so that is example number two. And then finally, we have example number three, magnesium. Now, the element magnesium has a symbol Mg. We did not just write Mg alone. We have a notation above it, 2 plus. Now, this is telling you that there is a charge present and the charge is positive. Now, what number was attached? Number 2. So it tells you that its oxidation number will be plus 2. That is rule number 1. The oxidation number of a monoatomic ion is equal to its charge. That is rule number 2, I beg your pardon. Rule number 1 says that an element in its pure state has the oxidation number of 0. And then the next rule says the oxidation number of a monoatomic ion, that is an ion with just one atom. A monoatomic ion is equal to its charge. What is rule number 3? Rule number 3 says oxygen is usually -2 in compounds. So when you have a compound, for instance, let's say you have H2O. The oxidation number of oxygen over here is -2. And I'm going to be showing you a process through which we can calculate the oxidation numbers of individual elements in compounds, okay? But the exception is that when you have a peroxide, like hydrogen peroxide, H2O2, the oxidation number of oxygen is usually -1. I'm going to show you how, okay? But for now, just know that usually in compounds, the oxidation number of oxygen is -2. Now, that being said, we have the next rule that says hydrogen is usually +1 in compounds. hydrogen is usually +1 in compounds. So for example, if we have a compound called H2O, all right, the oxidation number of hydrogen over here is +1, and the oxidation number of oxygen, as we saw in the previous slide, is -2 in compounds. Now, as we begin to solve for the oxidation numbers of individual elements, we'll be bringing all these rules together. Okay, so now here is this rule that says the sum of oxidation numbers in a compound is 0. The sum of oxidation numbers in a compound is 0. Now, let's go back a bit. This is where I want to explain something that I said earlier on. Remember, I said that oxygen is usually -2 in compounds. Now, there is an exception. In peroxides like H2O2, oxygen is -1. Why is oxygen -1, you may be asking? Now, let's calculate the oxidation number of oxygen in this compound. H2O2. Now, the rule that we just saw says that the sum of all the oxidation numbers in a compound is equal to 0. So it means that when you add the sum of oxidation numbers here, everything is supposed to give you 0. So let's use that rule and calculate the oxidation number for oxygen. Now, the rules also said that hydrogen in compounds has an oxidation number of +1. So we have hydrogen over here, which has the oxidation number of +1. Now we have 2 atoms of hydrogen. So that becomes +1 times 2 plus, we don't know the oxidation number of oxygen now, since that's the one we're calculating for. So let's name it X. And then we have 2 atoms of oxygen. So it becomes X times 2, all equal to 0. So altogether we have +1 multiplied by 2 gives us +2, plus X multiplied by 2 gives us 2X. Everything is equal to 0. So now we want to find X, so we're making it the subject of the formula. We take this 2 to the other side. So automatically we have 2X is equal to -2. When we divide both sides by the coefficient of X, which is 2, we have, this cancels this, X automatically becomes -1. So you can see the oxidation number of oxygen here being -1 as we have applied that rule. So we're going to be solving some examples where we get the oxidation numbers for elements in compounds. Now look at this second example over here that says hydrogen is usually +1 in compounds. So if we are asked to calculate the oxidation number of hydrogen in this compound NaH, we'll be applying all of those rules. So let's see all the rules first before we come back to this. We've seen this rule that says the sum of oxidation numbers in a compound is 0. Now look at this. For example, you have H2O. We want to see if this rule is true. Now remember, we said that hydrogen is usually +1 in compounds and oxygen is usually -2 in compounds. So now let's go ahead and add all of them together. We have +1 for hydrogen, and since we have 2 atoms of hydrogen, we'll multiply it by 2 plus oxygen over here, which is -2. So altogether we have 1 times 2 gives us 2. This bracket, when we open it, it becomes 2 minus 2, which is equal to 0. So you can see that the rule is absolutely correct, that the sum of oxidation numbers in a compound is 0. Next rule says the sum of oxidation numbers in a polyatomic ion equals the ion's charge. What do we mean? First things first, what is a polyatomic ion? A polyatomic ion is an ion that has multiple atoms inside of it, or multiple elements inside of it. For instance, we have this ion, the sulfate ion SO4 2-. So what we're saying is when you add all the oxidation numbers of all these guys together for sulfur and for oxygen, what you are supposed to arrive at is the overall charge. And the overall charge, I just circled it over here, is -2. So if we get the oxidation number of sulfur, plus the oxidation number of oxygen, and we have four atoms of oxygen, which is O times 4. What we are going to arrive at is minus 2. That is what the rule is saying. We're going to apply all these rules to get the answers for individual elements, okay? And then we have the next rule that says alkali metals, which are metals in group 1, always have plus 1 as their charge. They always have plus 1 as their charge. So now let's backtrack a bit. We saw an example in the rules that says hydrogen is usually plus 1 in compounds. So we have NaH. And they are saying in metal hydrides, hydrogen is minus 1. So if this compound is given to you and they say calculate the oxidation number for hydrogen, what are we going to do? First things first, we know that the sum of oxidation numbers in a compound is equal to 0. And now they are also telling us that alkali metals are plus 1. We just saw that rule now. So what are we going to do? The oxidation number of sodium plus 1 plus the oxidation number of hydrogen. We don't know what it is because that's what we're calculating for. So let's name it H is equal to 0. So we're looking for H. This one goes to the other side. So therefore we have H is equal to 0 minus 1. Everything is equal to minus 1. So you can see how we calculated the oxidation number of hydrogen to be minus 1 in these compounds. So that is the next rule that we saw. The alkali metals in group 1 always have plus 1. The next rule says alkaline earth metals, which are metals in the group 2 of the periodic table, always have plus 2. Examples like magnesium and calcium. Next rule says that fluorine has minus 1 in compounds. Don't get overwhelmed by all these rules, okay? We'll be applying them as we solve questions. And then next we say other halogens usually have minus 1 when combined with unless when they are combined with oxygen or other electronegative elements. So if you see elements like chlorine, bromine, or iodine in a compound, the oxidation numbers are usually minus 1 unless when they are combined with oxygen or more electronegative elements. Now, at this point, you might be asking, okay, so how do we calculate the oxidation number for elements um in a compound? So let me help you out with some rules that you can use. Rule or step number 1 equates the sum of oxidation numbers. Equate the sum of oxidation numbers to the overall charge. So we have the element or the compound, I beg your pardon, sodium chloride, NaCl. If I ask you over here now, what is the overall charge? The overall charge is 0 because there is no plus or minus that was identified above the sodium chloride symbol. So what are we going to do? We equate the sum of all the oxidation numbers to 0. So we're going to say Na plus Cl will be equal to 0. That is step number 1. Now, we are calculating the oxidation number of chlorine in NaCl. Remember, one of the rules that we stated is that alkali metals or alkali metals always have plus 1, and sodium happens to be one of them in the group 1 of the periodic table. So, the oxidation number of sodium, which is an alkali metal, is plus 1. And since we're calculating for chlorine, we don't know what it is. So we say plus Cl is equal to 0. So making this the subject of the formula, plus 1 goes to the other side. Cl will now be equal to 0 minus 1. The oxidation number of chlorine, therefore, is minus 1. I'm sure you got every bit of that. Don't worry, I'm going to solve another example. Here is example number 2. Example number 2 says, what is the oxidation number of sulfur S in this compound, H2SO4? Remember I told you, step number 1 always equates the sum of all the oxidation numbers to the overall charge. So my question to you here is, what is the overall charge? If you notice with me, there is no plus or minus anything there. So the overall charge is 0. So therefore, what we're going to do is to say H2 plus S plus O4 will be equal to 0. Remember, the compound is H2SO4. So we have H2, we have S, and we have O4. I'm sure you're following every bit of what we're doing in today's class. So the next thing to do now is to watch. Among all the rules, can you recollect anything that has to do with hydrogen and oxygen? Remember, we said that the oxidation number of hydrogen in compounds is usually +1. That the oxidation number of hydrogen in compounds is usually +1. So now let's put that out now. We have hydrogen, which is +1. How many atoms of hydrogen do we have? We have 2. So that becomes +1 times 2. Plus, we have sulfur, which is what we're looking for. We don't know what it is, so let's write it out. Plus oxygen. Remember we said, among all the rules, that the oxidation number of oxygen in compounds is usually -2. So we have -2. How many atoms of oxygen do we have? We have 4. So all of this is equal to 0. So therefore, let's put it out now. 1 times 2, we have +2 plus S plus this bracket here has -2 times 4. That gives us -8 is equal to 0. So now let's collect the like terms. This one can stand alone because it's the odd one among the lot. So we have S plus 2 minus 8 is equal to 0. -2 or +2 minus 8 gives us -6. So we have S minus 6 is equal to 0. When we take this -6 to the other side, we have S is equal to +6. So that is the oxidation number of sulfur. The oxidation number of sulfur in this compound is +6. Now, there is a way to check if your answer is correct or not. How do we check? Remember, we said that the sum of the oxidation numbers in a compound must be equal to 0. So if we add everything together, we will get 0. Let's do that. We have hydrogen, which is H2 plus S plus O4. If we add everything and we don't get the overall charge, which is 0, it means we are wrong. So hydrogen is +1. We have +1 times 2. The next is sulfur, which we have calculated to be +6. And then the next one is oxygen, which is -2 times 4. So let's see what we're going to get. 1 times 2 gives us 2 plus 6 plus -4 minus 2 times 4 gives us -8. So let's add everything together. This gives us 8 minus 8. That gives us 0. So you can see our answer is correct. The oxidation number of sulfur in this compound is 0. So next question says, what is the oxidation number of Mn, manganese, in KMnO4? So first things first, what we're going to do is to equate everything to the overall charge. What is the overall charge over here? It is 0. So we have K plus Mn plus O4 is equal to 0. What is the next thing to do? Remember the rules. This K is an alkaline earth metal in group 2 of the periodic table. So its oxidation number is +2. The rule says alkaline earth metals have the oxidation number of +2. Now we are calculating the oxidation number of manganese. We don't know what it is. So we have plus Mn and then plus, this is oxygen. Oxygen is usually -2. So we have -2 times 4, which is equal to 0. So let's calculate now. We have 2 plus Mn plus -8 is equal to 0. So we have 2 plus Mn minus 8 is equal to 0. So if we collect like terms, it now becomes Mn plus 2 minus 8 is equal to 0. So Mn minus 6 is equal to 0. Mn now becomes plus 6. So the oxidation number of manganese in this compound is plus 6. It tells us that manganese lost 6 electrons because it is positively charged. Now let's check if we are correct. If we add up the oxidation numbers of all the compounds together, we should end up with 0. Let's see if we're correct. So we have K plus Mn plus O4. The oxidation number of K, which is potassium, by the way, is plus 2. Plus magnesium is plus, manganese, I beg your pardon, is plus 6. Plus oxygen is minus 2 times 4, because we have 4 atoms of oxygen. So we have plus 2 plus 6 gives us 8. Then this becomes plus, in brackets, we have minus 8. Altogether, we have 8 minus 8. That gives us 0. So we are absolutely correct on this. The oxidation number of manganese in the compound is plus 6. So here are some practice questions that I want you to try out. And we've come to the end of today's lesson. I want you to get the oxidation numbers of all these elements. First one we have, calculate the oxidation number of nitrogen, N, in the compound ammonia, NH3. Okay, I want you to calculate the oxidation number of chromium in this compound. Okay, remember I told you that the sum of all the oxidation numbers must be equal to the overall charge. So let's take, for instance, we have Cr2O7 2 minus. Question I'm asking is, what is the overall charge of this compound? You can see it indicated over here. It is minus 2. So that simply tells us that when we add all the oxidation numbers together, it's going to give us the overall charge. So we have Cr2 plus O7 will be equal to minus 2. Let me even go ahead and solve that. So we'll be on the same page because I didn't solve any example that had an overall charge being minus 2. So now we don't know what the oxidation number of chromium is. So we have Cr2 plus the oxidation number of oxygen in compounds is usually minus 2. So we have Cr2 plus minus 2 times 7. Everything is equal to minus 2. So Cr2, we have plus. This is going to be minus 14 is equal to minus 2. When we open brackets, we have Cr2 minus 14 is equal to minus 2. Taking this to the other side, this 14 to the other side, what we have now is Cr2 is equal to minus 2 plus 14. So we have Cr2 is equal to plus 12. Cr2 is equal to plus 12. So how do we get the oxidation number? Now, remember, we have 2 atoms of chromium over here. So to get the oxidation number for chromium, we divide both sides by 2. So when we do that, now we are left with Cr. Chromium is equal to plus 6. The oxidation number of chromium in this compound is plus 6. So I just did that for clarity's sake. So go ahead and solve all these questions, and I'll be seeing you in the next class where we get to see more concepts concerning the redox reaction. I'm sure you enjoyed every bit of today's lesson. For those of you who are part of the live class, don't hesitate to ask questions for anything you're confused about. My DM is open, and I look forward to seeing you in the next class. Until then, I remain your favorite chemistry tutor, David, who takes the mystery out of chemistry so you can make history. Bye for now.